Hi there, Dr. Tishan here, and in this video we are going to find particular solutions to differential equations. This is going to be a two-part video. We're going to do 3 examples in part 1, and then I'm going to do 4 more examples, different style of examples in part 2. So we're going to just jump in and do some examples, and we'll just learn how to go through the process through doing some examples. A differential equation, we're going to do a first order differential equations. We're going to solve our differential equations, and we're going to actually write our answer as a function, as y equals when we're done. So you'll learn this in a calculus class or differential equation class. It's probably where you're going to use this topic. So first order differential equation in example 1 that's given to us, dy dx is x over y. The initial condition is 3, 4. And we want to solve it. So differential equation is a derivative equation. It's a rate of change. And so to solve a differential equation, we want to find the function. We want to break it down, find the function. To go from derivative to function, you're going to have to use the operation of integration. You're going to have to integrate. Before we can integrate here, though, we have to isolate the variables, separate the variables. Okay, so we have to get the y's on the left side of the equation with the dy, and the x's on the right side of the equation. When you set up a single integral, when you do the integration, you can only integrate one variable at a time. So you have to separate the variables. So we're going to first look at the differential equation and figure out what kind of algebraic technique we use to maybe separate these variables. All right, so we do have a proportion here, and one of the properties of proportions is that they're cross products. Cross products of proportions are equal if you have a true proportion. So to separate the variables, get the y's on one side, the x's on the other, just cross multiply here will take care of separation of variables for this example. So we're going to multiply this way, so you're going to end up with y dy on the left side, okay? And then we multiply this way, you have x times dx on the right side, okay? So, and there's our separation of variables done in one step, okay? So you've got the y's on the left with the dy, the x's on the right with the dx. Once you separate the variables, then you're going to want to integrate both sides, okay? So your differential equations, you're going to have 2 integration problems, two integration in one problem, all right? So, but we first have to separate the variables, right? We cannot set up a single integral, all right, with 2 variables, okay? So you have to separate the variables, put the y's, dy's on the left, really put everything else on the right, and then we'll go ahead and integrate. Okay, so once you integrate the left side, integrate y dy, you get y squared over 2. All right, integrate x on the right side, you get x squared over 2. All right, and then these are indefinite integrals, so don't forget about the constant of integration. So don't forget to put your plus c. All right, so right now we have an expression to represent the general solution. This is a general solution for our differential equation. It's not the particular solution yet, but this is a general solution, okay? So all curves in this form will have a rate of change equation, dy dx is x over y, all right? We want to find the particular solution given the initial condition we have here. So we want to find the actual solution that passes through this point 3, 4. So what we're going to do, okay, so, and this is usually the step where I work this out, is you have options, you can do this later on in the problem, but I'm going to use the initial condition 3, 4 to find c. Okay, so we're going to use the initial condition to find c. So I'm going to take this equation right here. I'm going to take 3 and substitute it in for x. 4 is going to get substituted in y, and we're going to solve for c. Okay, so we have 4 squared over 2, okay, equals 3 squared over 2 plus our constant. So this is 16 over 2 is 8, okay, equals 9 halves plus our constant. You need to subtract 9 halves from both sides. So 16 halves, take away 9 halves, and you have 7 halves, okay? So this is what our constant of integration is. We can plug a number in for, we're going to plug 7 halves in for our constant of integration, okay? So we have now y squared over 2 equals x squared over 2, all right? And then we're going to take the c and change our constant to 7 halves. We computed our constant to be 7 halves. All right? So now all we have left to do here, okay, this is our particular solution, but let's go ahead and write it as a function. Okay, so let's write it as y equals. So to write as y equals, let's take every single term in this entire equation, both sides, multiply by 2, okay? Y squared over 2, so multiply by 2, you get y squared, okay? Distribute the 2 here, multiply by 2, you get x squared, all right? And then multiply by 2, you have 7, all right? And so we have y squared equals x squared plus 7. We don't want y squared. We're going to solve for y. So how can we get y? Well, and these can be tricky. You have to be careful with these radical problems because when you do take the square root, you end up with a positive negative of the radical, okay? Now, is this going to be positive or negative? It's not going to be both if we write it as a function, okay? So will it be positive or negative? Well, now you got to look at your initial condition, and you have to notice that, well, we need to generate a positive y coordinate with our function that we have to generate. So because the y coordinate is positive, then when you do take the square root of both sides, your function notation, you're going to have the positive, not the plus and minus, the positive of x squared plus 7. So here is the function, all right? Here is the function answer to this differential equation given initial condition 3, 4. We want the positive root, all right? You take the square root of both sides, yet you do get plus or minus, but because the y coordinate that we need to generate is a positive, we want the positive root. So your answer to example 1, y equals the positive root of x squared plus 7. All right, so here's example number 1. All right, let's take a look at example number 2. Example number 2, dy dx, this is our derivative notation, first order differential equation, so it's a first derivative, is 6x plus 1 over 2y. So there's our differential equation. Initial condition here is 2, negative 3. So we want to go ahead and solve the differential equation. So we have the derivative, we want the function. So to go from derivative to function, we have to integrate, but you can't integrate two variables. You can't integrate two variables, okay? It's not possible to do that. You'll learn later on, Calc 3, when you start dealing with multivariate, you'll learn how to set up double integrals, triple integrals, but for right now, we don't do single integral. You can't integrate, you can't set up an integral with two variables, all right? So we can integrate one variable at a time, not two. So separate the variables, separation of variables. We want to move the y's on the left, the x's on the right, okay? So y's and dy's. So is there an algebraic manipulation here that we can do to separate the variables? Well, again, we have a proportion, okay? Because this will be similar to example 1, but there's a little different thing that's going to go on. Again, there's a proportion, and so if it's a true proportion, cross products are equal. We can separate the variables here again by cross multiplication. So multiply this way, you have 2y dy. Right, and then you multiply this way, you have the quantity 6x plus 1. So the quantity is 6x plus 1 in dx. Okay, so separation of variables, do whatever you need to do to get y's on the left, x's on the right. Okay, all right, so then we integrate both sides. Okay, once you separate the variables, once you separate y's on the left, x's on the right, you can set up an integration. All right, integrate 2y dy. When you integrate 2y, you get 2y squared over 2. The 2's here will cancel, won't they? So you just get y squared when you integrate the left side. All right, the right side, integrate 6x. You get 6x squared over 2, so that's 3x squared. Integrate 1, you get x. And then don't forget that constant of integration. Okay, so here we are. So y squared equals 3x squared plus x plus our constant. All right, what to do next? This is the step, and it's optional. You don't have to do here, okay? But in this step right here, I like to use my initial condition to find that constant of integration, okay? So I like to use, I'm going to use the point 2, negative 3 to find my constant, okay? So I'm going to use it right here. So this means I'm going to plug 2 in for x, negative 3 in for y, okay? So I have negative 3 in for y, and I want to square that, equals 3 times 2 squared plus 2 plus my constant. All right, so I'm here, okay? Let's compute this. Negative 3 squared, negative 3 times negative 3 is 9. Order of operations, so 2 squared is 4, 4 times 3 is 12, so 12 plus 2 plus constant. So you have 9 equals 14 plus your constant. Subtract 14 from both sides, so 9 minus 14 is a negative 5. So my constant of integration is a negative 5. All right, so that's going to be substituted in for right here. All right, so we have y squared equals 3x squared plus x, and then my constant of integration is negative 5, so we're here. All right, now we want to write our answer as a function. Okay, so y squared, this is not function notation yet. We want to write it as y equals, not y squared equals. So what we need to do is we need to take the square root of both sides. When you take the square root of both sides, it generates a plus and minus, a positive and negative. It generates a plus and a minus, and so what we need to do here is we got to look at the y coordinate to see, is it going to be the positive of the root or the negative of the root that we need? Because the y coordinate that we need to generate with this function is negative, then you actually need the negative of the radical. Okay, so y is going to equal here, take the square root of the left side, you get y, and when you take the square root of the right side, okay, we are going to want the negative of the radical, the negative, not plus or minus, just the negative of 3x squared plus x minus 5, and here's your answer. Okay, so this is the answer to example 2. All right, now let's take a look at these two, both of these at the same time. Okay, these two first examples. Okay, so similar but different, aren't they? All right, so similar because both, cross multiply. All right, and then when we integrate both sides, we ended up having a y squared term. All right, so we ended up needing to go ahead and take the square root of both sides, all right, to write this in function notation. All right, when you take the square root, okay, so if x squared, equals 9, then x equals plus or minus 3. When you take the square root of dealing with variables, you have the positive, negative. We're writing this as functions, so we can't express the final answer as positive and negative. It could just be positive or just be negative. Which one, though? You have to look at your initial condition. Look at your initial condition here. Your initial condition, if the y coordinate is positive, then your function has to generate a positive number, so you want the positive of the radical. If your y coordinate is negative, then your function needs to generate the negative y coordinate, so you're going to just not plus and minus, but you're just going to deal with the negative of the radical. Okay, so here's an example of differential equations, finding particular solutions with radical expressions. All right, and then I have one more example on the backboard, which is going to introduce the concept of exponential, and we'll do more with the exponential in part 2 of the video that I'm going to make here. All right, so let's go ahead and take a look at example number 3. I'm going to just flip the board to the other side so we can take a look at example number 3. Here we go. So example number 3, dy dx is x times y. Our initial condition here is 0, 3. And we want to find our y equals. We want to solve this differential equation. Okay, we want to solve it. It's a derivative, we want the function. How do you go from derivative to function? We'll need to integrate, but we can't integrate yet. You can't integrate two variables. When you set up a single integral, you can only integrate one variable at a time. So before we integrate, we must separate the variables. We must take the y's, dy's, move to the left, x's, dx, move to the right. Okay, so y's, dy's. So multiply by dx here. Let's start by multiplying. So multiply both sides by dx, and so you have dy equals x times y dx. So multiply both sides by dx. Okay, almost there. We got to move this y over. So divide both sides by y, and you get 1 over y dy on the left. And on the right side, you have x dx on the right. Okay, so here is your separation of variables. Here it is. All right, once you have the y's, dy's on the left and the x's, dx on the right, we can go ahead and integrate both sides. We can integrate now because we have the single variables on the left, single variables on the right. Integrate 1 over y. Okay, so when you integrate 1 over y, remember that rule? That's your natural log absolute value y, isn't it? That's natural log absolute value y. Right hand side, integrate x, and you're going to get x squared over 2, and then plus your constant. Okay, so you're going to have this, all right? Now, this is a little bit different because remember that when we're all done with this, we have to write our answer as a function, okay? We need y equals, not the natural log of absolute value of y equals. We need to have y equals, okay? So right here, before we deal with our plugging in for our constant, right here, I want to try to get the y by itself, okay? So if you have natural log of y and you need to get the y by itself, what can we do to get the y by itself? Okay, so what we can do to get the y by itself is you're going to have to raise both sides. You're going to have to use exponential to undo a logarithm. Okay, and I have videos out on this also. Okay, so if you want to brush up on logarithmic functions, exponential functions, and solving those. All right, but to undo the logarithm, we're going to need to use exponential functions. So I'll show you how that works. Let me just rewrite this step right here. So you have natural log absolute value y equals x squared over 2 plus a constant. So what we want to do is we want to take both sides of the equation, okay, and we want to do the e raised to the both sides of the equation. So e raised to the both sides of the equation here, okay? So let me move over here. I'm running out of space. That's why I did this one on this side, okay? So I'm moving over here. So what do I have here? On the left side, I have e raised to the natural log absolute value y. And on the right-hand side, I have e raised to the x squared over 2 plus a constant. So I have this, okay? So this is what I need to do, right? Now, if you remember your properties, e raised to the natural log, anytime you have e raised to the natural log of a quantity, then it's equal to that quantity, okay? So, and because I have exponential on both sides of the equation, I don't even need to bring down the absolute value signs anymore. I don't need them, okay? Because your range for exponential functions are positive real numbers, and because the range is positive, I'm going ahead and protecting that absolute value, that positive, all right? Right-hand side, now we have to play around with the algebraic concept of your laws of exponents, okay? So the right-hand side, we want to split this up. We want to call this e raised to the x squared over 2 times e raised to a constant. We want to split this up. If you remember from an algebra class, keep the base, add the exponents. That's your rule for exponents, okay? Keep the base, add the exponents. So we're undoing that, aren't we? Okay? So keep the base, add the exponents. When you take it apart, you're going to end up here. Okay? Now, why would we do this? Because this right here is a constant that's going to be dropped out front. Okay? So, and this is helping us put our exponential equation in standard form. Standard form for an exponential equation is going to be y equals ce to the kt power, okay? So we want to get the constant out front, all right? Now, so c is our constant of integration. So when you take e and raise it to the c, you're going to have a constant still, but just to give it a different representation, I'll pull it out front and call it a c sub 1, e to the x squared over 2. So here is our general solution to this differential equation. We've got it. This is our general solution, but we want the particular solution. The particular solution is going to come once we find out what our c value is. Once we know what the exact curve is what it looks like passing through this initial condition 0, 3. So we need to find, we need to go ahead and find, right off to the side here, okay? So we need to find c using our initial condition 0, 3. Okay, so we're going to find our c value and then we'll be done. So how do we do that? Well, you're going to take 0 and substitute it in for x. Okay, we're going to take 3 and we're going to substitute it in for y. So you have 3 equals c sub 1 e to the 0 squared over 2. Okay, so 3 equals c sub 1 times any number to the 0 power is always 1, isn't it? Okay, e to the 0 power is 1. So our constant of integration is just going to be 3. That's what our constant is. So we write this is our general solution. Let's make it a particular solution passing through our initial condition. So y equals our c sub 1, we computed that to be 3, okay? And then it's e to the x squared over 2. Okay, and here is your final answer. This is generally the way that you're going to handle your exponential growth problems. So this is how you're going to handle the exponential growth problems. When you have a integrate, you get a natural log, and you need to use your exponential laws of exponents to work through these. All right, so this is the first of 2 parts, in case you want more examples of finding particular solutions to differential equations. We're going to do some more, we're going to do more radical, more exponential, and I'm going to do some fraction problems in the next video. So thank you for watching, and I hope this helps you with all your endeavors in mathematics, and best wishes, good luck to all of you. Thank you. Bye-bye.